All right, this chapter is going to be about energy flow and how it goes through different stages and also how it works in our systems. So energy by definition is going to be the capacity to do work. We can have all different forms of it, mechanical, heat, sound, all sorts of different things. If you were to study energy, that study is called thermodynamics. It's a very involved study. It's pretty awesome if you can do that. And we measure it in kilocalories. Now, you've heard of calories before. Those are actually going to be a unit of heat. And so, by definition, what a calorie is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So the way that they actually do that is they have this calorimeter, and they can put the substance in there. They're just trying to figure it out, and they heat it up and calculate how much energy goes in to raise the surrounding water by 1 degree Celsius. So that's kind of how that whole process works. Another energy unit you might hear about a lot is a joule, and a joule is equal to 0.239 calories. So just to give you that information. So there are going to be two types of energy that we can have, kinetic and potential. Kinetic is going to be the energy of motion, so moving things, and potential energy is stored up energy. So I've got some sweet picture here. So potential energy, this ball is not moving yet, right? It's at the top of the hill, so it has the potential to go, but it hasn't moved yet. Whereas kinetic energy would be once you push the ball and it actually starts moving, right? So same thing, if I were to hold a marker up here in my hand, that would have potential energy, and when I let it go and it moves, it has kinetic energy. So as far as potential and kinetic energy go with our systems, we can say kinetic energy would be like muscle spasms or contractions, right? And potential energy we have in chemical bonds. So we're basically all day, what you're doing to stay alive is you're breaking the chemical bonds that you've ingested and using that energy for kinetic energy to keep you alive. Okay. So when we get into that whole process, which don't worry, that's an entire lovely chapter, we are going to talk a lot about oxidation and reduction. So hopefully you remember that from the previous chapters, where oxidation is when you lose an electron and a reduction is when you gain an electron. Now obviously we talked about the fact that electrons are not just going to be like, I don't want to be near that anymore, I'm just going to hang out here by myself, right? They don't do that. So if something is getting oxidized, something nearby must be getting reduced, right? So they're always kind of going to go together. So since they go together, we're going to call them redox reactions. And so a lot of the processes we're going to talk about are actually going to be redox reactions. So reducing power is going to come up too, and that's going to be the ability of an organism to store energy by transferring electrons. So redox reactions, remember when we talked about the mitochondria and we said, that's for cell respiration, and you were like, I don't know what cell respiration is, but I'm going to memorize that, right? Well, what cell respiration actually is what's keeping us alive. So mitochondria are really important, and so what's happening on all the little membranes of those guys are going to be a bunch of redox reactions that we're going to talk about in the next chapter. So really, really going to be important to understand that process. Now, this is also important. The closer an electron is to the nucleus, the less energy they have, right? So if you think about it, that makes sense with a lot of things, right? The further away it gets, the more energy it has. So if I had like a ball on a rubber band here, and I was just kind of lightly spinning it around, it probably doesn't have that much energy, where if I were to let go, it's probably going to go a little far, but not super far, right? Whereas if I have that same ball on the same rubber band and I'm just whipping it around and it's further away from my hand because it's stretched, and I let that thing go, I'm probably going to break a window or somebody's face or something like that, right? So the closer the electrons are to the nucleus, the less energy they have. The further away, the more energy they have. So what can happen when we talk about photosynthesis is sunlight can actually add energy to an electron and cause it to get further away from the nucleus, okay? And so that process is important because then that energy can be used to break or form chemical bonds. Okay, so laws of thermodynamics. We're going to talk about these two laws of thermodynamics. First one, energy cannot be created or destroyed. It can only change one form to another, okay? So the amount of energy is constant. It's just changing from one form to another. In the notes, you might hear me say some energy gets lost as heat. That does not mean that it goes into la-la land and we have actually lost it. I just mean as far as usable energy goes, it's been lost and we lose it as heat. For example, mammals are really, really bad at energy loss because we're warm-blooded. And so we actually lose a lot of heat to the environment. We use a lot of the calories that we ingest just to keep our body temperature up. Whereas something that's cold-blooded doesn't lose as much heat to the environment because it doesn't matter as much. And so they can actually sustain themselves on a lot less calories. Okay? So then the second law of thermodynamics is going to be that the disorder of the universe is constantly increasing. And if you could see the rest of my house right now, you would totally understand that one. So disorder is more likely than order. And that makes sense, right? If I had a whole bunch of markers that were like, you know, all the colors of the rainbow and I just dropped them, it would be pretty creepy if they all dropped lined up from, you know, Roy G. Biv order or something weird like that, right? It's more likely that they're not going to end up in that ordered state. Okay, so free energy, that's going to be the amount of energy that's available to break or form chemical bonds. And so there's this formula right here about free energy. So G is free energy, H is going to be energy in chemical bonds, T is going to be the temperature, and S is the amount of energy unavailable because of disorder. All of those can be calculated. So if you think about it, H is energy in chemical bonds. When things are all nice and bonded together, that's a lot of order. It's very orderly, right? So H is actually the amount of order around, and T and S, temperature, if we increase the temperature, that's going to get things flying around, and that's going to be disorderly, right? And S is actually a measurement of disorder. So this is going to be disorder. So you're basically subtracting order from disorder and seeing how it comes out, okay? So going along with that, you can have what's called an endergonic or an exergonic reaction. So if G ends up being positive when you do that equation that I just showed you, then you're going to have an endergonic reaction. And what that means is you're going to have to put energy into that situation to get the reaction to happen. That's going to be different from an exergonic reaction. Exergonic, think exploding, right? And so that's going to be a reaction that releases energy because G is negative, okay? So if you want some examples, at endergonic reaction, one that requires energy, have you ever played around with those chemical ice packs? That's a perfect example. So those chemical ice packs have two chemicals that are separated, and then you crack it, and what happens is it starts to feel cold. Well, the reason it feels cold is because that reaction requires energy to do that, and it's pulling the heat from whatever you have it on to do that, right? So that's an endergonic reaction. An exergonic reaction is going to be one that releases energy. So think of like fireworks, right? Exploding, right? Giving off heat, giving off light. That's going to be an example of an exergonic reaction. So in the next video, we're going to talk about activation energy and how that works as far as enzymes go.